Hi everyone, my name is Mariana and I work as a computational linguist at Grammarly. I'm happy to see so many people here interested in natural language processing. Today we are talking about meaning representation for natural language understanding. And our main focus today would be how to formalize something as abstract and as unstructured as meaning, right? So what we are going to talk today about is, first I'm going to do a small introduction to meaning representation, because this is a hobby of mine, and I'm not sure that more people in the audience have the same kind of hobby, right? And then we're going to dive into details of abstract meaning representation, which is just one of the semantic parsing formalisms that we can use to represent meaning of a natural language. Let's find our intuition first. How do we humans understand each other? How do we understand the meaning of a sentence? Well, first of all, we know what words mean, right? In the context, it's easy for us to disambiguate what a word means. Second of all, we don't communicate in words. We communicate in like full sentences, and words in these sentences interconnect. So we know in what relation the words are with each other. And we know that from the order of words in the sentence, and we know that from the form of the word, and so on and so forth. Then we also usually know the context of the sentence, so we don't communicate in isolated sentences. We usually know which sentence preceded the current sentence that I'm uttering. And also we know a whole lot of things about the world around us, so we know what meaning is probable and what meaning is not probable, etc., etc. And that's why situations like this almost never occur in the real world, right? Because if somebody tells you have a seat, you usually know that they are inviting you to have a seat, not just to take a chair in your hand. Well, usually in the real world, we also use nonverbal communication, like the posture, or like gestures, or your mimicry, and so on and so forth. But we are going to talk about text today, so I'm just crossing out nonverbal communication for us in this context. How can we teach a computer to understand and decipher the meaning of the sentence in the same way as we humans do? So let's start with something like really primitive at the beginning. First of all, here's our toy text. Children wanted to eat all cookies, and they were delicious, right? How can we find the meaning of this sentence? The easiest thing that we can do is to find important words here, right? And there are many algorithms in natural language processing that will help you find these important words. And in our case, this will be like child, cookie, eat, and delicious. Does this represent the meaning of our text? Who thinks it does? Well, yeah, kind of. So you people are right, because if we are solving a task of topic modeling or a task of text classification by topic, this bag of words, important words in the text, does represent the meaning of the sentence. It's not sufficient for other NLP tasks, because if I switch the words in the sentence, and now we have cookies wanted to eat all children, and they were delicious, right? So the meaning of the text changes, but the topic of the text stays the same. So it all depends on what task in NLP you're solving. As I mentioned, if we just find the important words and use this bag of words approach, and then you can represent these words as vectors, find the mean vector there, and do whatever you want to do with them, it's sufficient to represent the meaning of the text for some tasks in NLP, but not for the tasks of natural language understanding, which we're going to do next. So the question that arises is, can we do better? And Mr. Lomberg from Office Space says, I think we can do better than that. And I agree. So the next thing that we can do with the text is do syntactic analysis of the text. What you see on the screen is a dependency tree that I built with a spacey dependency parser, and it shows us some relations between the words in the sentence. And these relations represent the syntactic role of the word in the sentence. So now you can see that the word children is a subject of the word wanted, and then that the word cookies is an object of the word eat, right? So it gives us some more information about what role the words play in the sentence. But it's not like that good, because we can see, for example, from this very tree, that children is not the subject of the eating, right? Child is not the subject there. You have to go from eat to wanted and see that they are related to, and then from wanted to children to find who is the doer of this action, right? And in reality, if we look at more sentences like this, we will find that the doer, the one who does the action, is not always the subject in the sentence, and the action in the sentence is not always presented by a verb. And also, we can paraphrase the same meaning with many, many, many different ways, and we would ideally want to have the same presentation for them, because we're talking about meaning presentation, right? So if I paraphrase this sentence, children wanted to eat all cookies, to, for example, children's wish was to eat all cookies, you can see this phenomenon that children is no longer a subject of anything, and the action of wanting is now represented with a noun, with wish, right? So now we have the same question. Can we do better than that? Well, of course we can, and this is the topic of our presentation today. So for many, many years, computational linguists around the world are working, or have been working on finding a good way to represent the meaning of the sentence. And you can see many, many like unknown words for you on this slide, like universal conceptual cognitive annotation. Like, what is that? You know, why are even people working on some weird things like that? So don't worry, we're not going to go through all of these scary things. I'll just show you a couple of examples of how meaning can be represented. And then we will go to a hobby of mine, abstract meaning representation, and dive deeper into that. So let's look at typed lambda calculus expressions. So the idea of presenting a sentence, the idea of typed lambda calculus expressions is to represent a sentence as a logical expression. And when we are transforming the sentence into a logical expression, we can use all kinds of logical connectors. We can use quantifiers like existential and universal quantifiers here, and then, you know, find a logical expression that will be equal to true if all of these logical components will be equal to true. Where is lambda calculus type expressions used? They are used for question answering systems in NLP. So, for example, you're building a question answering system, and you can actually phrase the same question in many, many different words, right? In many different ways. You can ask what is the capital of Germany, or which city is the capital of Germany, and so on and so forth. But you usually want to find answer to this very same question. You need to find an entity that is that with Germany has a relation of capital. So there are semantic parsers that you can use to do that, and you can actually parse these sentences into these lambda expressions that will map the entity to a truth value. And these lambda expressions are usually organized in tuples. You can see a predicate here and two arguments, which is very, very handy, because our knowledge bases, where we are looking for an answer for our question, are usually RDF bases, right? So they work in these triplets. So you can map your predicate to the relation in the RDF base. And you can find an answer, for example, Berlin, or usually it's like a list of answers that you can then re-rank and so on. You can find a parser like this, for example, in the Stanford library. It's not a default component of the Stanford Core NLP library, but if you go to the webpage of the Stanford group, you can find a SAMPRI parser that parses sentences into logical expressions. And as all of the semantic parsers, like such parsers are built on dependency trees. So usually a dependency tree, like the one that we saw before, so you usually extract triplets from these dependency trees, triplets of dependencies, and map them to predicates, and then use an optimization algorithm to write a parser like that. Oh, sorry. I pressed something else. Can I go back? Yeah. This is a new thing for me. So a different formalism, a different way to represent the meaning of the sentence is called semantic role labeling. The aim of semantic role labeling approach is to find who did what to whom. So say we have a sentence, the police officer detained the suspect at the crime scene. We can put it in the passive voice. We can create a relative clause here. But we have the same semantic roles in each of these three paraphrases. So we have the detainer, we have the detainee, and we have the location where this action happened, right? So, but you can imagine that if we create such semantic roles, like for every verb in the language, we will have a gazillion of different semantic roles. Because if we take a verb like to want, then we have a wanter, we have the thing that is wanted, and we may have a beneficiary. Because if I want happiness for you, then I'm the wanter, happiness is the thing wanted, and you are the one who is getting the benefit from what I am wanting, right? If we take the word eat, then we have a semantic role of eater, and we have a semantic role of meal. So in order to formalize this somehow and structure these semantic roles in some way, computational linguists designed like this notation with arguments. So usually the one who is doing the action, the agent, is marked as arg0. Then the thing that is going through this action, usually called theme in theoretical linguistics, is marked as argument 1, and so on and so forth. So, and then maybe additional arguments for different frames. One of the ontologies that contains this information is called prop bank. So prop bank contains more than 7,000 frames for the English language, and each frame describes a concept with semantic roles that this specific concept, this specific action can have. And there are also additional roles like time or location or manner of the action or causation of the action, cause of the action, and so on and so forth, that are verb independent, that can occur with any kind of action. So semantic role labeling has already become part of standard libraries. For example, LNLP, one of the recent NLP libraries, has semantic role labeling module. And you can see if we feed our sentence to LNLP, it finds that children are actually arg0, meaning like the eater, for the action to eat. Because in our sentence, we have two actions. We have an action of wanting, an action of eating, and we have semantic roles for each. Semantic role labeling is usually formalized as a classification task. So we usually build a syntactic tree. Usually it's a tree of consistency tree. And find all predicates in this tree. So we find wanted and we find eat. And for each predicate, we collect features for each phrases that are used in this tree, that occur in this tree, and we classify them. Like, so we found the phrase children, we have the predicate to eat, we collect all possible features that will be like parts of speech, that will be lemmas, that will be like the path from eat to children through the tree, and so on and so forth, the depth of the tree. And we then can classify that children plays the role of arg0, meaning like the doer of this action. Semantic role labeling is widely used in NLP for tasks of information extraction in all possible domains. Like if you're finding criminals, in newspapers and you want to know who killed whom. Or if you're working in the financial domain and you want to know who filed the lawsuit against whom for which sum of money, where it happened, when it happened, what happened next, and so on and so forth. So semantic role labeling is a fantastic approach. It's very simple, but it also has its drawbacks. So we saw this couple of examples that were paraphrases, where we defined the same semantic roles for the same actors of the action. But if we paraphrase it with nominalization, like if we say children's wish was to eat all cookies, then we wouldn't be able to find the phrase children, because children's wish would now be a phrase, and we won't be able to assign a semantic role there. So it works in most cases, but not for all cases. And the representation that we're going to do to talk about today is called abstract meaning representation. The main idea here is to abstract away from words and work only with concepts, right? Which can help us with all kinds of paraphrases. So our sentence, children wanted to eat all cookies, that can be paraphrased in multiple ways, like eating all cookies was what children desired, right? I think many people in the audience can relate to that, to cookies. I know I can. So all of these paraphrases of wanting, wanted, somebody's wish was, or felt like, or desired, can be represented as the concept of wanting. You can see like want, 0, 1. 0, 1 means like the meaning of the word want. Then you have argument 0 and argument 1. Who is wanting children, what they are wanting, the event of eating, and the event of eating has to happen by children, and the children are eating cookies. But we will go through that in more details in a second. Okay, so I hope you got the motivation why we're working on meaning representation for natural language understanding tasks. Let's now explore our abstract meaning representation graphs, our AMRs. So each sentence is represented as a rooted, you can see it's rooted with this top on top, rooted directed, you can see that there are arrows everywhere, and a cyclic graph, like this one here. Nodes in this graph are concepts, and we're going to discuss what concepts mean again. Edges are different semantic relations, like arguments that we discussed, and also these additional relations like time, location, and so on. And in AMR, there are about 100 different relations that are specified that can be used. And also, all functions words are thrown away because we're working only with concepts. So if we take a sentence, I beg you to excuse me, this is one of my favorite examples for AMR, then I and me will be the same concept in the tree, in the graph, in the AMR graph, here I, and then we can like show relations. So in this case, we have like two events, begging and excusing. For beg, I is the doer, and you is the one undergoing the action, and then for excuse, you is the doer, and I is the one who is undergoing the action. Okay? Good. So nodes in AMRs can be either prop bank frames. So this is something that we saw before, right? So prop bank, this large ontology that has frames for different kinds of concepts. It can be just a word, like we had I and you in the previous sentence. And it can be a special keyword, because AMR embeds the information about named entities. So if you have organization that is under some name, you won't encode the name of the organization directly. You will create a node that will represent the concept of organization, and then add a specific relation of name there. So AMR is cool because it handles all kinds of stuff. So it handles semantic roles, it handles entity types, it handles coreference. Coreference meaning that if I say something like, I beg to you to excuse me, I and me are the same concept. So me refers to I, and there's a special task in NLP that is called coreference resolution that resolves that, and AMR notation embeds that. It also handles modality and polarity. We're going to look at that. And wikification. So for each named entity that you encode in AMR, you can also add a link to the Wikipedia article and solve entity linking task, for example. AMR doesn't handle tense of the verb. I mean, definiteness and plurality of nouns. This is, some people consider this a drawback. This was done for practical reasons. And so far, I don't think everybody struggles that much about that. But we will talk about natural language generation, well, where this matters, this information matters. AMR uses Penman notation, the one that you briefly saw before, where each node is assigned a variable. So Penman notation has been used for many years for different representations of different graphs, and it was just adapted to be used for AMRs too. And there's a very nice parser for Penman formats in Python that you can use, and it's freely available open source on the web. So we create a node for the concept of bagging, and we assign a variable. A variable is generated automatically from the first character of the concept. If there are many concepts with the same first character, then like just an index is added. This is just for technical information. You don't need to pay attention to that. Why we need this variable is for us to be able to reuse them in this Penman format. So you can see I beg you to excuse me. This means that we can reuse variable y and variable I in the event of excusing and not create a new concept. And that's how you can parse. After that, you can parse like this Penman format with the available parser into a graph structure. Just to explore AMR a little bit more, so here are a couple more different representations of the same concept of wanting, desiring, having a desire, be desirous of, and so on. And they all of these paraphrases will be represented by the same AMR graph. And we can see that believe has the same letter as boy, so we just create a B2 variable here, so it's not confusing. Polarity in AMR. So in order to express negation in AMR, there's a special semantic relation that is called polarity, and it's assigned, it has a special concept with a minus. So we have the soldier was not afraid of dying, was not afraid to die, or didn't fear death. In all of these cases, we have a concept of fear, and the soldier is the doer of this concept of fear, and he's afraid of the concept of dying, which will be performed by this soldier. And the polarity will be a minus. Modality in AMR, so there's a concept of modality in linguistics that represents the likelihood of the event or the obligation of the event happening or the probability of the event, the willingness, and so on and so forth. So modality is like a huge section of linguistic research, and it can be expressed with modal verbs in the English language or with adjectives or with modal nouns and so on and so forth. You can also say it is an obligation that the boy not go. So in order to express like must, since it expresses obligation, we skip the modal verb. We just put the context of obligation as the focus of our AMR graph. And then we can say that we don't know who is obligating. That's why we don't have arg0. And we don't know who is being obliged. That's why there's no arg1. But there's arg2 because we know the topic of obligation. And the topic of obligation is that the boy not go. So this is what you can see with the subgraph with go. And go is in meaning two, meaning like disappear or leave, because go in the first meaning will be to go into some direction, right? So we would need more words here. AMR is also adapted to work for question answering systems, and that's why in AMR you can find a special type of node, a special type of concept that is called AMR unknown, that you can see here on the graph. So in this case, we have a question, which state borders with Kansas, and we have the event of bordering. We both states are actually entities, so we create for them concepts of state, and we know the name of the second state, but we don't know the name of the first state. So this is how we can embed the information of the question into an AMR. If we paraphrase the question, and now we have a polarity question, for example, like does Texas border with Kansas, then we actually know both states' name. We have Texas and Kansas. What is unknown to us is the polarity, right? We cannot put a plus or a minus. This is where we would get our AMR unknown concept here. OK, and like one more example, just to get you understand AMR more. So we have 14,000 people fled their homes at the weekend after a tsunami warning was issued, the UN said on its website. So we have the focus of AMR graph is saying something. This is the main event. Who is saying something? The organization under the name UN. It's saying something, talking about fleeing, and fleeing is done by people of quantity 14,000, so everything is normalized here. And they are fleeing their homes, so we can see coreference resolution here, because we are reusing the variable that we created for the word people here. And we have two temporal semantic relations. So in the text we have after a warning was issued. Actually, to issue a warning is just a paraphrase of to warn, right? So we have an event of warning about tsunami, and the medium by which the message was delivered was the website. And again, we can see coreference resolution because we have the variable O here, so meaning its website. So its website is organization's website. Okay, so now we know how AMRs, what AMRs look like, and now let's just understand how can we actually automatically build them, right? Because you can agree that even to annotate them manually takes a lot of cognitive processing from people who are working in this domain. Well, this is meaning this is difficult. So the first question that you might ask me is, where do you get the data, right? We're at the data science conference. So we get the data from AMR banks. There are actually a couple of corpora available now. The first corpus, the first story that was annotated with AMR is The Little Prince. I think you all are familiar with that story. Then, you know, the developers of this notation and the NLP community get really excited. And after that, they annotated 40,000 sentences of different newswire and web forums and so on and so forth. And there's even a corpus of CNN transcripts that also have summaries, so for summarization tasks. And there are like 7,000 sentences of BioAMR, because there's an active research in event extraction from bio domain. And AMR is also used for information extraction too. This is just for you to get excited. This is a famous sentence from The Little Prince, from this first corpus that was annotated with AMR. You become responsible forever for what you have tamed. There's a very nice semantic relations here for extent of your responsibility. So extent of your responsibility is forever, right? The concept is of forever. And so on. So you can clearly browse the corpus if you are interested in how people represent these sentences, the story of The Little Prince using AMR. AMR parsing, so there are 4 algorithms for AMR parsing that are being developed, that have been developed in the last couple of years, because AMR is like very fresh. It appeared only in 2013, but the first parser appeared only in 2015, and it wasn't very good. So people are actively working on that, and recent parsers have become better and better. So we're going to talk briefly about graph-based and transition-based algorithms that can be used to build these AMRs. We're not going to go talk about rule-based algorithms because they don't work very well for AMRs. Since this is meaning representations, it's not scalable enough. And there have been like maybe 2 papers on seek-to-seek approaches for AMR, which showed much worse results, so we're not going to go there too either. What is needed to do AMR parsing, like the standard NLP pipeline? We need part-of-speech tagging, syntactic parsing, named entity recognition, and coreference resolution to be able to map the people and their homes, that their and people are actually the same node in the meaning representation. So graph-based parsing has pretty simple intuition. There's a JAMR parser that is open source and available on the web, where it works in 2 steps. The first step is to identify concepts. So say we have this toy sentence here. Kevin Knight likes to semantically parse sentences, as you and I here, right? So we run our named entity recognition, and we know that Kevin Knight is a person. So we can create, in a rule-based approach, a node of person that has a name, Kevin Knight. Then likes is the verb, and we have a whole corpus that is annotated by prop bank, like these ontological relations. So we just do this as a sequence labeling task. Semantically is matched to a concept of semantics. Do is just deleted because it's a function word, we don't need it. For example, the word parse, it's a verb, so we definitely want to make a concept of it, but it's not present in the prop bank, because prop bank was developed way before the word parse appeared as a verb, so actively used. So we can just create parse 0, 0, meaning that we don't know to which frame to map it, but we know that it's a concept, and then we have a simple literal concept sentence. After that, we create a dense graph So we just match all nodes with all nodes, right? And for these edges, we can predict weights. How can we predict weights? We have an AMR bank. And from our AMR bank, to predict the weight of this edge, we can collect features from this node, collect features from this node, and features include parts of speech, lemmas, frames in the prop bank that we work with, the syntactic parsers, coreference, and so on and so forth, like everything that we get from our NLP pipeline. And then we can train the algorithm to have weights, right, on our AMR bank. And then we can assign for each of these edges a score, like some score that it has. And after that, we can run a very famous and widely used algorithms of defining a maximum spanning connected graph to find like the best way, the highest scoring graph in this connected graph out of this dense graph. And here's BAM, here's our AMR, right? So these parsers work a little bit better than the next algorithms that I'm going to show you, but they are, in the worst case scenario, their speed will be like quadratic time, right? So the next idea would be to build a transition-based AMR. And you may have noticed that AMR graphs look a little bit similar to dependency parse trees. If you haven't, I'm going to show you. Okay. So here's our sentence. I beg you to excuse me, and this is the dependency tree. And this is the AMR. So I also made it flat so that you can see the relations. And we can see that bag has a subject relation to I, an object relation to you, and an open complement relation to excuse. And we see the same kinds of relations in the AMR graph, but just with different labels, right? Then with excuse, we would have to work a little bit more, because excuse has a relation to to, which is a function word, and we want to throw it away. It also has a relation to me, which should be the same concept as I, like you see below. And it doesn't have a relation to you, so we have to add this relation to. So you might get the intuition that we can simply take a dependency tree and do a series of transformations to get an AMR graph out of it. So this is what CAMR parser does. This is another open source AMR parser that you can find on the web. It transforms the dependency tree into an AMR. So we just traverse the dependency tree, again, at each node where we are and at each edge that we are observing. We collect all kinds of features that we get from our NLP pipeline. And then we train a classifier that decides what to do next, like to merge nodes or to swap nodes or to delete a node. In this specific implementation, there are only these 8 things that the classifier, these 8 actions that the classifier can predict for you to do at this particular point of the dependency tree, because you're traversing it, right? But there may be like other implementations too. So for example, if we have the sentence, police wants to arrest somebody, in the dependency tree, we only would have the word want with a relation to police and arrest. But in AMR, we also need to have this reentrance. We also need to know that the police are the doers of the arresting, right? So your classifier may predict that at this particular point, you need to do a reentrance. So reentrance is one of the classes, one of the actions that the classifier can predict. How are AMR parsers evaluated? So there's an evaluation metric that is called Spatch. Spatch means semantic match. So you take your AMR graph, and then you take out all of the triplets. And you can do this with the same Penman parsing library that I mentioned earlier. And you find like all of the concepts and all of the relations. And then you can just calculate precision, recall, F-measure, anything you want, only on instances, only on the relations, on labeled relations, on unlabeled relations. So there are like modifications of this metric depending on what exactly you're interested in. Maybe you're interested in identifying named entities only, or preserving named entities only, and so on. If we talk about like the quality, so currently graph-based work better than transition-based because since you build this dense graph, you can find like long-distance relations better, right? So, graph-based algorithms currently reach up to 70% of F-score using this Spatch metric. But speed-wise, transition-based algorithms are much, much faster because they work, like in worst case, in the linear time. You just traverse the tree once, right? You don't have to do this searching of the maximum spanning connected graph. And I have a couple more minutes just to give you a brief explanation of where AMR is used. So the application of AMR. AMR, in the last 3-4 years, AMR has been widely used in different areas of natural language understanding tasks. This will be like natural language generation, information extraction, text summarization, you see have been pretty active, and text summarization tasks, especially abstractive text summarization. AMR has given the really good results for this task, and even better than the latest paper on abstractive text summarization using BERT. So, and also like question answering, machine comprehension, so all kinds of tasks that needs you to understand the text. Let's do a brief like demo, not demo, but like example. Look at the brief example of natural language generation. So this is a quite a complex AMR graph. You can see that the focus of AMR graph are like two actions. You have and on the, as a focus, so there are like two events. One event is that the country, and you can see Wikifcation here, that is Bosnia and Herzegovina, that is mentioned as Bosnia in the original text, remains probably divided on some ethnic topic, right? And then the second event is the violence, the concept of violence, that happened during a major football match, right? Something like that. And it happens here, and occasionally, which gives us some intuition about the tense of the sentence, that it was like, for example, a present tense or something. And we'll also have information about the time that these two events happened following a war from 1992 to 1995. So in 2017, there was a shared task on natural language generation from AMR. And the reference sentence of this graph was following the 1992-95 war, Bosnia remains ethnically divided and violence during major football matches occasionally occurs here. So this is quite a complex sentence in the complex AMR graph. These are the outputs of the two top winning systems in this competition. So the first one did pretty well. Following the 1992-1995 war, it even inserted a comma, you can see that. Bosnia has remained. You can see the difference in tenses, right? Because AMR doesn't embed the tense, so the system has to guess the tense. Has remained an ethnic divide, which is a very nice and also like correct paraphrasing of ethnically divided, right? So you embed the information about the meaning in the graph, and then the output can be all kinds of paraphrases of the same meaning. But then the system screwed up a little bit because it said, and the major football matches occasionally violence in here. So in the place of violence, there should have been some kind of verb, but the system couldn't generate it, so that's why the sentence gets a little bit screwed up here. So the second winning system also screwed up the second clause. So, and the first clause a little bit, because it says Bosnia remains divided in ethnic what? We don't know what exactly. So, and the occasional football match, this is totally incorrect because occasional shouldn't modify the football match. It modifies the action, right? In major violence in here, and then it got completely gibberish. But it's still pretty impressive, I'd say, because we don't have a good solution for controlled natural language generation in NLP right now. And so the idea of natural language generation with AMR is that you can extract rules of tree-to-string matching from AMR banks and use these rules as features for a transducer, and then you can train this transducer and use the statistical machine translation kind decoder to find like the best transductions of these graphs to real sentences, and then you can pick the highest scoring sentence with a language model. And rules can look like this. Like if you have in your AMR bank the concept of writing with two arguments, you can find like that x1, it maps to a real sentence that says x1 writes the x2. But if you have the role of destination, it can map to x1, takes a write to something, and so on. So these rules can be used for further transduction, and then a language model can help you find the highest scoring sentence. But here you can ask me a question like, okay, we learned to change sentences, transform sentences into AMRs and AMRs into sentences. Like, why do we need this skill, right? Actually, you do, because if we mention again this abstractive text summarization task, you can solve it pretty cleverly with AMR. You can take all sentences in the document, build AMR graphs, then merge them into one mega graph, then find a summary graph, right? That will be like an optimization task. And from the summary graph, you can use a natural language generation algorithm to generate a summary. And let me show you a small example. So I saw Joe's dog, which was running in the garden. The dog was chasing a cat. So we can build two AMR graphs, merge them together, extract a summary graph, and then generate a summary. Joe's dog was chasing a cat in the garden. And there's a pretty simple intuition here. So we build a document level AMR by just merging everything. So we find that in two sentences, the concept of the dog is the same, so we can merge these two nodes. Together, we can create an additional root node that will join all of the AMRs in the text, because they have to be connected, right? And then you can do some kind of graph expansion here. So connect every nodes that are connected but not directly, just to expand the search for this summary graph in the end. And then when you're looking for the summary graph, you just predict important nodes, predict important edges, and ensure the result is the valid graph. Ensure that you haven't picked like the highest scoring edge that doesn't connect the highest scoring nodes, because otherwise it will just keep dangling in your graph. You don't want that, right? And you can use these AMR banks that are, and their summaries, the AMRs of their summaries, to use as a training data. So I hope that you now feel that you know AMR, like Neo knows Kung Fu. I also added some useful references at the end of the presentation and links to the software, so that I mentioned on the way, also like AMR parsers and summarizers and generators, like anything that you want to do. The slides will be online, I promise. Yep, so thank you for your attention, and let me know if you have any questions.
My name is Mariana, and we have a lot of questions for you.
A lot, really?
A lot.
Can AMR process new terms, misspelled words? How? No. This is a short question. Because, well, if you add a spelling correction in your NLP pipeline and you do spelling correction beforehand, then you don't need to care about this problem. But this is the same problem for all NLP tasks. Like if you're doing syntactic parsing, you have to statistically predict the label and the dependency to a word that the system has never seen before. So it just, has to work in some way. So in AMR, you will just a little bit back. So in AMR, if you will see a misspelled word, if it's predicted as a verb, then you will create a concept of a verb, which you cannot map to anything, but it will still be a concept and have statistically probable relations. If it's tagged, for example, as a noun, then most probably you will get a literal string that will maybe be merged with some other misspelling of the same word, like same misspelling of the same word. So like that. Is AMR currently the best choice for some of the most NLP tasks? If we are talking like the best, then I only found evidence for abstractive text summarization, it being the best. But I cannot say the same for other tasks because I haven't done like very thorough research, because like summarization was in focus of my research and other tasks have not. You can look like for this information yourself, I'd say. In general, can grammatically correct real sentences be generated from AMRs? Yes and no, because you will still rely on language modeling. And language models are very, very different. And if you have your favorite language model that helps you predict grammatical sentences better than non-grammatical sentences, then yeah, the chances of generating a grammatically correct sentence go higher, let's say like that. How select top node for analysis with AMR? How the top node for analysis is selected. So, like, why say is top node in example? Why say is top node in example? Okay, yeah, that's a good question. So, the top node, since all of these semantic parsers are built on top of dependency parsers, you usually pick the main verb from the dependency parse tree, and this will be your top focus. So, in that example sentence, you said 14,000 people fled their homes, UN said. So, actually, the main sentence, the main clause of this sentence is that the UN said that 14,000 people fled their homes. So since it's the main verb in the dependency tree, it will be the focus of an AMR. Are there any problems with languages which differ from English? Not yet. AMR is currently available only for 5 languages, and if you Google AMR eager with one word, like AMR eager, then you can find a demo of AMR for 4 languages. I think it's English, German, Italian, Chinese, and some other language. And for other languages, there haven't been reported any differences because they also cooperate with concepts. The problem, though, may be with low-resource languages because not all languages have such a vast variety of ontologies that can be used to represent concepts and that can be used to annotate this much data. So that's the problem, of course. Does AMR work for any human language? Well, it does. English, for example, and 4 more than I noticed. Performance on large documents. If you're talking about text summarization, I hope, because AMRs are built on the sentence level, right? And you can merge sentence level AMRs into a document level AMR. And here you don't care how long the document is. It will just extend the length of your document. Although in order to optimize the search for the most meaningful sentences, people who do research with text summarization with AMR pre-select the sentences, like using some heuristics, because there are like a lot of heuristics that you can use, that the sentence contains a named entity, for example, then there's a higher chance that it's important, or that the sentence has a high TF-IDF score, or like more important words, to say it, to put it mildly. Then you can pre-select the sentences, build, again, an AMR of the whole document of these pre-selected sentences, and then look for a summary graph. But so there are many optimization techniques, but this shouldn't be a problem.
Last one question.
Yeah. How to handle relations between sentences in text that contain more than one sentence. Sentences that contain more than one sentence. Maybe you mean like more than one clause or something. So if you mean more than one clause, then you saw this example that I was showing for natural language generation. You usually have a conjunctions between them, right? So because I know I like turtles and Yura like cats. So here you have two clauses in one sentence. You would have and, like the conjunction in the focus of this AMR graph, and then two events, described with subgraphs of this graph.
Folks, make some noise for Mariana. Mariana, many thanks for you.
Thank you so much.